Thank you, and I would like to first thank Katja and Knut for the kind invitation to give this talk. It's a great pleasure to be here. Yeah, so my topic for today is stability and a little bit about uniqueness of an inverse problem for this semilinear wave equation. And this talk is based on joint work with Matti Lassas, Toni Liimatainen, and later Potensioni Macchiato. So the setting where I will work will be on a n+1 dimensional globally hyperbolic Lorentzian manifold n. So here Lorentzian just means that we are in space-time, and global hyperbolicity means that there is no singularities in the manifold and there is no closed time-like loops. So there is no time travel. And in this talk, I will assume that the manifold splits into space and time. So n is of the form r times m, where m is a n-dimensional manifold, and this r plays the role of time. And the metric here is of the form minus a positive smooth function beta times dt squared plus a family of Riemannian metrics h, which depends smoothly on time. And since I will be working with the wave equation, I need the wave operator, which I denote by box. And wave operator is defined in local coordinates by this formula. So this is not so important. What is this formula for us? So if you would like to work in Euclidean space, then this wave operator is just the standard wave operator. So dt squared minus the Laplace operator in r times Rn. So this is the setting. And we are now working with the boundary value problem. So for this, let the omega be a smooth, compact submanifold with boundary of M. And we don't need to make many assumptions on omega. So this set could be non-convex. And now we are interested in recovery of a potential function Q in this nonlinear wave equation here. So we have the wave operator box on U of time and space plus potential Q of time and space times U to the power M. And this we consider on this finite time interval from 0 to capital T times omega. And here this nonlinear power M should be an integer greater than or equal to 4. So I will mention later why we need this assumption, but probably what we are doing would work also with M equal to 3, but then we need to make some more assumptions on this set omega and some more geometric assumptions. So for this talk, I will assume that M is greater than 3. Right, so then on the boundary of the manifold, we assume that U is equal to F. So here 0t times boundary of omega is the lateral boundary of manifold. And then we have 0 initial values, so U and time derivative U at time equals 0 vanish. And for the inverse problem, we need measurement data. So for us, the measurement is the Dirichlet-Neumann map, lambda, which is defined as usual as the mapping which takes the boundary value f to the normal derivative of u on the lateral boundary. So here we take the normal derivative where u is the outward normal of the lateral boundary. And I'll make a notation sigma for the lateral boundary. So sigma is 0t times the boundary of omega. And maybe I can comment that we have this mapping property for the DN map, which is somehow a statement about smoothness. So the DN map maps from the Sobolev space HS plus 1 to HS. So if you think naively that the derivative should drop the smoothness by 1, and then we take the trace on the boundary, we would lose half derivative. But actually, the DN map only loses 1 derivative. So the small statement about smoothness, but this is classical. So DN map will play the role of measurement for us. And the inverse problem is now to recover this potential function Q from the DN map. And particularly, I'm interested in how stable is this reconstruction process. So if I make some small error in measuring the DN map, then how big error do I make in my reconstructions? And before I go to the statements of the theorems and proofs, maybe I mention some earlier results. So uniqueness for the linear wave equation, dp squared minus wave speed c squared times Laplace operator, is quite old already. So this was considered by Belishev and Kurilev in the 80s and 90s. So here they had a variable wave speed, and the question was, can we recover this wave speed uniquely? And the answer is yes, by some boundary control methods and Totaro's unique continuation principle. But quite recently, in 2014, Kurilev, Lasses, and Ullmann showed that if the equation has some nonlinearity, then this nonlinearity can be used as a tool for inverse problems. And this made these nonlinear inverse problems really fashionable. And since then, there has been so many people who are working in this field. So I've listed here some, and I apologize for anyone who I missed. There's so many people working in this field now. Okay, so unfortunately, we cannot recover this potential Q in all of the space-time. So this is because the wave equation has this property due to the hyperbolicity that waves travel at a finite speed. So there are some natural limitations on where we can recover Q. So consider this domain where we are working, 0t times omega, and then we look at the future and past of the lateral boundary. And we take a compact set W in there. So in the picture, if the space omega is down here, time runs vertically up. Then when we send waves from the boundary, they travel on these blue lines, and this diamond set here in the middle is where we can make reconstructions. And here we assume that there is some small space between this time cylinder or this diamond set and this compact set W. So we are not at the boundary up here. Then our main result is this kind of technical statement that if we have two potential functions, Q1 and Q2, whose derivatives up to order s plus 1 are continuous, and they have this a priori bound, we know that they are bounded by some positive constant c in the cs plus 1 norm. Then we take the corresponding DN maps, lambda 1 and lambda 2, for the corresponding nonlinear wave equations. And with this, we have that if the DN maps are sufficiently close to each other, so if the difference between lambda 1 and lambda 2 in a Sobolev HR norm is less than some small number delta for all sufficiently small boundary values f, then we can find a constant c, which is independent of the potentials Q1 and Q2, independent of delta, such that the difference between the potentials Q1 and Q2 in subnorm in this reconstruction set W is bounded by constant times delta to the power sigma, where sigma is a positive number given by this formula. So this is now Hölder continuity, Hölder stability of the inverse problem. If the DN maps are quite close, so the error is small, size delta, then in the reconstruction, our error size is delta to the power sigma. And so this is our main result. And maybe I'll note here that we take the difference of the DN maps in some Sobolev space HR, where this R can be less than S. So S was the smoothness index of our potentials. So we don't require so much smoothness from the measurement. So this comes from some duality arguments later on. So the measurement can be rougher than our potentials necessarily. Okay, and the proof uses this very popular method of higher order linearization. So this method uses some small parameters, epsilon1 to epsilon m, where m is the power of the nonlinearity. So we put small parameters into the boundary data. So the boundary values q are epsilon1 times f1 plus epsilon2 f2 and so on until epsilon fm times fm. And then we differentiate this equation with respect to the small parameters. And the idea is that when we differentiate, this nonlinearity here gets linearized away. But because we are now working with noisy measurements, so the DN map may have some small error, then if you differentiate the DN map, the noise can just blow up and then we recover nothing. So to combat that, we will use finite differences to approximate derivatives. So I will denote by d epsilon m a finite difference with respect to the epsilons. And this is the standard forward finite difference operator. We are going to use that. So let's now differentiate this equation. So if we apply the finite differences on this nonlinear wave equation, we get the differences of box of u, and they are equal to this linear term. So the nonlinearity gets linearized away, and we get just minus m factorial times the unknown potential q times m functions v1 to vm plus then some small error term. This error comes from Taylor expansion of u with respect to epsilons. And also it depends on the finite differences. This error we can control. So really the main idea is that we had a nonlinear equation, and by differentiating, we can turn it into a linear equation. And these functions v1 to vm, they satisfy linear wave equations. So each of these satisfies box of bj 0 inside our time domain. Boundary values of these bj's are the same as we used for the nonlinear equation. So bj is fj on the boundary, and fj is one of these boundary values of the nonlinear equation. And bj's have vanishing initial data at time equals 0. So this is nice because these bj equations, they don't depend at all on the unknown potential q. That's good. So before we move forward, we need one more function, auxiliary solution to this backwards wave equation. So at V0 be such that box of V0 is 0, and V0 has vanishing Cauchy data at the top of the time cylinder when time is equal to capital T. V0 vanishes. So this will be helpful later on. So now we multiply our differential equation by V0 and integrate over all of this time domain and integrate by parts. Then we get that this Q times the product of the functions V0 to Vm, integral of that, equals integral over just the lateral boundary of the dn map. This dn map appears from the integration by parts. The box turns into normal derivative, and the normal derivative is just the dn map, plus then an error term here. And this integral now is over only the lateral boundary. So the top and bottom of the time cylinder, so when the time equals 0 and time equals capital T, they are absent. And the reason is that at the top of the time cylinder, we assumed that V0 is 0. This is the assumption of V0. And at the bottom of the time cylinder, these Vj functions have 0 data. So that's why we have only integral over the lateral boundary. And now this right-hand side is what we would measure in the practice. So we have measurements of the dn map, and we can take finite differences of that. And then we get this integral of Q times product of Vj's up to some error. And this would now recover potential Q if we can make this product dense in some suitable function space. And our choice is now to make this product of V1 to Vm approximate delta distribution. Because if this now is an approximate delta, then Q times a delta spike, integral of that recovers Q at some single point. So that's the main idea. So how do we choose these functions V1 to Vm? There are probably many choices, and we chose to use the Gaussian beams. So Gaussian beams are constructed by looking at the light-like geodesic gamma. So light-like means that it's a path which light would travel. And if S is now the geodesic parameter, then we will look at Fermi coordinates, because these are convenient coordinates for us. So the Fermi coordinates look like the geodesic parameter S, and then the vector in Rn. This vector is somehow orthonormal to the geodesic. And we use parallel transport to move this along the geodesic now. So then in these coordinates, the Gaussian beam is roughly an exponential of this form. So we have e to I times y1 times a large parameter tau minus positive number a times tau times y squared. So roughly speaking, these Gaussian beams are such that they have oscillating part to direction transversal to the geodesic. Here y1 is the first component of the vector y. And then we have exponential concentration on the geodesic due to this kind of Gaussian part. So Gaussian beams are wave packets which travel along these geodesics. And to get rid of this oscillating part, we will make the choice that if we have two distinct light-like geodesics, gamma 1 and gamma 2, they get their respective Gaussian beams, V1 and V2. And to cancel the oscillation, we let B4 be the complex conjugate of B1, and B4 be the complex conjugate of B2. So then, in our integral identity here, we have a product of B1 to B4. Then the oscillating parts cancel out in the product. And here, this tau parameter is somehow what causes our delta spike. So the tau causes exponential concentration. So this now at an intersection point of two geodesic causes exponential concentration at neighborhood of 1 point, or well, possibly many points if these geodesics intersect many times. But that's the main idea. So we'll talk a little bit about how we construct these Gaussian beams. So the Gaussian beams are constructed by using a WKB ansatz. So in these Fermi coordinates, Gaussian beam looks like a V of S and Y, where we have an exponential e to I times tau times a phase function theta of S and Y times an amplitude function A of S and Y. And we will now force this kind of ansatz to solve our wave equations approximately. So if you just plug in this ansatz to the wave equation, we get this kind of result. And now the trick is to make these terms here equal 0 kind of separately. So we start with this first term, and we try to make this equal to 0. And if we can make this equal to 0, then we know what theta, so the phase function, is. And then we can make these remaining terms equal to 0. And that gives us the amplitude function A. And we really do this only approximatively. So we try to make this right-hand side just small with respect to the large parameter tau. So this should be small in some suitable topology space. So let's make this first term here equal to 0 now. So this is just an iconal equation. And this we can solve by making an ansatz. So we make a guess that theta is a finite sum of theta j's, where each of theta j's is a homogeneous polynomial of order j in the y variable. And then we say that this inner product of differentials of theta vanishes to some order capital N in the neighborhood of the side-like geodesic if all derivatives of this inner product vanish on the geodesic. And now we just make a guess. So we start by saying that theta 0 is 0, theta 1 is y1, and then we see that, okay, this iconal equation is satisfied to first order, and this process can be continued up to higher orders. So this is how we solve the iconal equation. Then, so we know what theta is. Now we make the remaining 3 terms equal to 0, and this gives us the amplitude term. So again, to solve what is the amplitude A, we say that A should depend on this tau term, so reciprocals of tau to the power j. So if we plug in this ansatz to our equation up here, then we get a family of n plus 1 first order differential equations for A. So from these equations, we can recursively solve what is A. The first equation is just first order differential equation for A0, and these remaining equations depend on the previous solutions that we got. So that's how you construct Gaussian beams. It's a technical construction. So now our integral identity looks like this. We chose these Gaussian beams so that we get rid of the cancellations, oscillations here. And this B5 to VM solutions, we can solve almost however we want, as long as they are supported near the intersection of these two Gaussian beams. So V5 to VM, they can be, for example, equal to V1. So now we start working on V0. So this V0 just makes sure that at the top of the time cylinder, the contribution of the integral disappears. So we need to make sure that V0 has vanishing Cauchy data at time equals capital T. And V0 should be supported at the intersection of these two Gaussian beams, because we want to see this approximate delta spike. So for this, we constructed boundary optimal geodesics. So we say that a geodesic gamma is optimal if it goes from point P to point Q, and if the time separation between P and Q vanishes. So time separation is supremum of lengths of piecewise smooth causal paths from P to Q. So all optimal geodesics are like. So then we have a lemma that we can construct boundary optimal geodesics. And here are these special geodesics such that if we pick an interesting point X inside our manifold, so X is, for example, the intersection point of our two Gaussian beams, then there exists a future directed optimal geodesic from the boundary to the point X, or vice versa from X to the boundary, such that this optimal geodesic intersects the boundary, lateral boundary, transversally. So the idea here is that because this geodesic now intersects the boundary transversally, then this B0 function, if it's a Gaussian beam traveling on that geodesic, then it really shoots out of the manifold before it meets the top of the time cylinder. So these are boundary optimal geodesics, and I have a picture here to show what's the idea. So let this brown cylinder be our time domain. Here we have omega times time. Then we pick an interesting point X inside the manifold, and we consider the light cone of the point X. So it's this blue double cone here. And we look at the intersection of the light cone with the lateral boundary. Here, these black curves, they are the intersections of the light cone with the lateral boundary. And then we take either the latest point, Z-sup, or the earliest point, Z-inf, on this intersection. And these points are now suitable for our optimal geodesics. So if we now shoot optimal geodesic from Z-sup to X, then the intersection of that geodesic with the lateral boundary will be transverse. And the same if we shoot a geodesic from X to Z-inf. That will be intersecting the lateral boundary transversally. And so the point is, this B0 function will travel along the geodesic from X to Z-inf, and it will shoot out of the manifold for meeting the top of the time cylinder. So this is a technical thing that we do. But now there is this small obstacle that two light-like geodesics in general can intersect many times in general globally hyperbolic Lorentzian manifolds. So if we have chosen these two geodesics, comma 1 and comma 2, and we have their corresponding Gaussian beams, then we can look at the possible multiple intersections of these geodesics. So let x1 to xp be the intersection points. Then instead of getting delta spike at one point, we get this approximate deltas at each of the intersection points. So this approximate identity integral will be constructed actually recovers Q at each of the intersection points xj. So we just recover a sum of values of the unknown potential. And now the question is, how can we extract this potential Q from this sum? So here we need to make some more clever choice of these B0 functions to make this reconstruction. So we can show that it is possible to choose these functions B0. We can choose P B0 functions so that they vanish at the top of the time cylinder, and so that this kind of separation matrix, which contains these B0, 1 to B0P functions here at each of the intersection point x1 to xp, this matrix is invertible. So we go back here, this way we get, if we use these P functions, Vj's, we get a linear system of equations where this coefficient matrix containing V0 functions at the intersections is invertible. So that recovers this vector of values Q. But unfortunately, that's not quite enough for us, because if we now make a small perturbation of these points x1 to xp, so we try to recover the potential Q at some different points, then these functions V0 will change. And in principle, because there are infinitely many points in the manifold, we would need infinitely many functions V0. And that's a problem for stability, because we don't want infinitely many anything to do stability. So we can show that there exists a finite family of these V0 functions, so that we can pick from that finite family P functions which separate any possible intersection points. But before I show that, let me show what's the basic idea of these V0 functions. So in this picture, we have these two light-like geodesics, comma 1 and comma 2, and the black lines here. They don't look like geodesics, but I assure they are geodesics in this picture. They intersect at 2 points, x1 and x2. And now we have this exponential concentration at these 2 points, x1 and x2. And we would like to recover Q from this information. So we choose a boundary optimal geodesic, this red line here, corresponding to x1, boundary optimal geodesic. And we shoot a Gaussian beam backwards in time along this geodesic. And clearly this geodesic does not meet the point x2, which is further in the future. So this first boundary optimal geodesic, the Gaussian beam, it picks up the value of potential Q at x1. Then we move to future and we shoot another boundary optimal geodesic through the point x2. We shoot the Gaussian beam V0 backwards in time. And now this picks up the value of Q at x2. And we don't really care what happens to this geodesic in the past. Because, okay, if this geodesic goes somewhere in the manifold, we don't care. If it hits this point x1, then, okay, we don't care either because we already recovered Q at x1 by this first geodesic. So that's the idea of this separation matrix. And I'll give here just a more precise statement of what I said before. So we can construct a finite family of functions V0 so that if we have any p points, x1 to xp, which are sufficiently far apart from each other, then for these points, we can pick from this finite family M p functions so that the corresponding separation matrix of the Gaussian beams becomes invertible. So this says that any p points can be separated by using this finite collection of Gaussian beams. And this is good for stability. Okay, but there is one final technical problem that, okay, what if our intersection point happens on the lateral boundary? Because so far we have constructed these delta spikes inside the manifold. And actually this is something that Katja Krupczyk asked from me in the private correspondence earlier. So this is a good question. So if the intersections happen on the lateral boundary, then part of our delta spike would lie outside of the domain of integration. So somehow we lose some information if that happens. But it turns out that's not a problem. So if part of the delta mass is outside the manifold, then we just need to modify our approximate delta spikes a little bit. So we need to renormalize them to take into account this missing delta mass. So in this lemma, we have a Lipschitz function B, which plays the role of the unknown functions Q1 and Q2. And then we take the usual approximate identity, so B times an exponential. But because part of this delta mass is outside of the domain of integration, we are integrating only over the upper half plane here. And to take into account this missing part of the approximate identity integral, we renormalize by kind of error function here. So this is a technical statement, but we can fix this problem of missing mass at near the boundary. So then we can show that this integral now, when tau goes to infinity, converges uniformly to this function B. So boundary intersection points are not a problem. So from this, we can then combine all of these results. So everything that I did so far can be done uniformly with respect to the intersection points of our like geodesics. So these intersection points don't matter. And we now just need to optimize with respect to all of the parameters that we introduced. So there were these parameters epsilon1 to epsilon n that we used for the finite differences. There is the large parameter tau, which we used for construction of Gaussian beams. And then there is the error that we make in the measurement of the DN map. So we optimize all of those so that the error is as small as possible. So we get that the error term here is of Hölder type. And so from the DN map, we get this kind of integral, which contains these approximate delta spikes. This integral recovers values of the potential Q at each of the intersection points of our geodesics. Then we constructed invertible coefficient matrix of functions V0 at each of the intersection points. And we know that the error is Högler type. So this now recovers potential Q. And if we take the error to 0 in the measurements, then this recovers the potential Q uniquely. So that's everything I have to say about this. So our results are on arXiv. Thank you.
Thank you very much, Teemu, for the very, very nice talk. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself. Any questions or comments? Okay, if not, thank you very much, Teemu, for the very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you very much.